So last time we want to see another applications of Bolobash set pair inequality in terms of for intersecting families. And here the convention is when we say intersecting family, we mean the sets in this family are pairwise intersecting, not meaning that they have a common elements. So this is lecture 18, I believe. This is 17, right? Okay, the theorem we want to prove is this theorem. This is a result of myself with Balog, Delcourt, Das, and Charizade. About 10 years ago, we proved that the number of maximal intersecting K-uniform families on the ground set 1 to n is at most this quantity. So what's surprising about this bound is that we've seen the total number of intersecting families is at least 2 to the n-1 choose k-1 by just taking subfamilies of a trivial one. And as you can see here, if you think about k fixed and n goes to infinity, this is polynomial in n. So we have an exponential in n quantity, lower bound for all intersecting families. But here, this is polynomial in n for the number of maximal ones, the subcollection. So polynomial versus exponential, that's a huge difference. The idea is to introduce this so-called generating family. The key idea is using this generating family, we can somehow introduce a set pair that satisfy the hypothesis in Bolobash set pair inequality. So let's recall the definition of this generating family. First, we introduce for every K-uniform family, we define this script I, the curly I of F, to be all the K-sets that intersect the sets in F. Okay, so all those K-sets that intersect all elements in F. Then it's simple exercise to see that a K-uniform family is intersecting if and only if F is a subfamily of this I of F. And it's maximal intersecting if and only if F equals to I of F. This is a simple exercise. I will leave it for you to verify, exercise 1 and exercise 2. Here's one of the key lemma saying that no matter which maximal intersecting K-uniform family we're given, let's say F, then we can always find the generating sets, which is a subfamily of F. This is a definition, such that it satisfies what? Let's write down this. Such that, first of all, why it's called generating set? Because if you take this, if you generate a family using this I operation, you will recover F. You can generate F. This is why it's called generating set. Second of all, I mean, just having the first one is not interesting because I can simply take G to be F. And we know this is true for maximal intersecting family. What's important is that G, we get a small generating set. Maybe let me write small here. And the size of G, the number of K-sets in G, is at most 2K choose K. So this is again quite surprising. Let me make a remark. Because it could very well be that our family, it's possible that it could have size n-1 choose k-1. It's possible, right? The largest one. But to generate this family, no matter what maximal intersecting family it is, we just need to take a subfamily of it, and you generate this family, you can recover, and this subfamily we take has no n in it. Has no this parameter of the size of the ground set in it. This is quite surprising. But the size of its generating family is independent of n. So let's see the proof of this. The proof is very simple. We sort of described this is the key lemma. The proof is we start removing elements from F one by one while maintaining, let's say you get smaller and smaller, while maintaining that this family, when you remove one by one, it's still a generating set of F. So I of Fi, when you keep removing it, you still get the original family. So keep removing sets from F to form, so let's say F0 is F F keep removing sets one at a time from F to form a nested sequence. At the beginning, we get F0, and remove 1, we get F1, remove 2, F2, so on and so forth. Okay? Such that for area I, Fi is a generating set for F. At the end, it must stop somewhere because F is a bound finite size. Let's say at the end, we stop at F prime. Let me just F prime. Let's say stop at T times. This is the final family. You must stop somewhere each time you remove one. So the number of steps T is at most size of family, which is finite. So we stop. Good. This is a valid operation. T is well defined because F0 satisfies that, right? By exercise 2, F0, which is IF, satisfies that. By exercise 2, T is well defined. Good. Now we're going to argue that we're going to take G to be the final family is what we want. All right. Well, trivially, G is the final family. It's a subfamily of our original family. And by our definition, I of ft, which is I of G, satisfying that it generates F by definition. So we just need to prove that G is small. So by construction, G is a generating set for F. So that's not a problem. We left to show that G is small. It's at most 2K, choose K. All right. So okay. Now let's write out the G. Let's say the elements in G is F1, F2, dot, 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 F R or Fs. Yeah, Fr. It has size R. Then the key observation is that the minimality of G implies what? Implies that for any I in R, maybe I should write it in a different line. The minimality of G implies that if you remove anything from any element from G, you take a smaller one, and if you generate a new family, it's going to be strictly bigger than the family that G generates, which we know is F, right? That's the minimality. For otherwise, if this two is the same, if you remove something, and these two are the same, then we should keep going. We should take this Ft minus this Fi. You should take a smaller one. It still generates the whole thing, right? And remember, when you take a subfamily, what it generates is larger. It's the opposite. We mentioned it last time. So this is a key observation. What does this mean? That the family that this generates, it's a proper superfamily of F. That means there is something that's in here, but not in here. Okay? Meaning that there exists a K-set. Let's call it GI that's in here. But not in here. Okay? What does it mean GI is not in F? That means there is something in F disjoint from GI, because if everything in F intersect GI, then GI should have been added to F by the maximality of G. Okay. No. this is not the point I want to make. Give me a second. What I want to say is, right. Okay. So, what I want to say is, because G is in here, GI is in here, by the definition of this generating operation, GI should intersect everything in here. By definition of this generating family operation, GI intercept Fj is non-empty for any j not equal to, for any Fj in G minus Fi, where G is not I. Okay. But on the other hand, we must have GI intersect Fi itself is empty. For otherwise, so let's see. If GI also intersect is, if it's not empty, what does it mean? Yes. For otherwise, GI intersects all sets in G, right? We already know it intersects everything by Fi. If we also intersect Fi, then you intersect everything in G, which then means by definition, it lies in Ig, which will mean this will imply GI is in Ig, but we know Ig is F. This is a contradiction because GI is not in F. So we are done because we've now built this FIGI family, F1G1, FRGR. For each I, Fi, we get a pair Gi that's destroying from it by intersecting all other Fj. So this is what we want. They are disjoint, but all the others are intersecting. Okay. Then Boloba's set pair inequality implies what? The total number of pairs R, which is the size of G, is at most the uniformity of F plus uniformity of G, this family, choose uniformity of one of them, but they are all K uniform. So it's K plus K, choose K. Finishing the proof. Any question? Then we are done, because to prove this bound for all, look at this collection of all maximal intersecting K uniform family. For each one of them, we apply this lemma. Each one of them, we apply this lemma to get a generating family, which is small. This is an injective map, simply because this generating family should recover the family F. That means the number of maximal intersecting family is at most the number of generating sets of size at most 2k choose k. And to bound the latter, we simply use the total number of sets of size up to 2k choose k, which is this bound. So this is an injective map. That means F can map to G, where this G is from the lemma. Okay, so IG equal to F, and G is small. So the number of maximal one is at most the number of sets of size at most 2k choose k, which is at most the desired quantity that we wrote down. All right. Let's reformulate this. We mentioned last time that we can reformulate Erdős-Corrado in terms of independence number and upper bound in the Knaser graph. So this lemma, we can also rephrase it. This lemma in terms in the Knaser graph. So in Knaser graph, before writing it down, let's see how this lemma will look like in Knaser graph. In Knaser graph, an intersecting family is an independent set, and maximal intersecting family is a maximal independent set. Okay. And the generating set, it's a subfamily. So we have this F, which in Knaser graph, in the vertex set of in Knaser graph, this F subfamily, which is a subset of vertices, which is a maximal independent set here. We can find the smaller one, G, also independent set, which is generating set. What does generating set means? That means we can order F1 to FR, the sets in G, and we managed to find G1 to GR such that G1 is disjoint from F, GI is disjoint from FI. When they disjoint in Knaser graph, we put an edge between them. And GI intersects all other FI, all other FJ. When they are intersecting in Knaser graph, we don't put an edge. So this is precisely an induced matching. A matching between Fi to GI, where we call induced matching because there's only these matching edges, no other cross edges. although we don't care what happens in GI and what happens in FI. Okay, so let's write out. In Knaser graph, the FI, GI, I in R set pair it looks like you have F1, Fi, Fr, G1, GI, GR. You have this edge because they are disjoint, but you don't have all other edges. No other edges. Although we don't care what happened inside. Inside, we don't care. Okay. Corresponds to two sets of vertices so this is G. Let's call this G prime. G and G prime, such that between G and G prime, we have induced matching. Okay, good. And if you go through this proof of the lemma, you will see that we can define an invariance for this parameter. We can define this so-called bipartite induced matching number. The bipartite induced matching number of a graph G denoted by nu bi of G is the maximum number R such that there exists a R matching UIVI I in R such that UI is not adjacent to Vj for any I not equal to J. All right. We don't care the edges inside UI nor the edges inside VI. That's why this is called bipartite. Because if you further require this to be independent sets, the whole thing is called induced matching. Bipartite version means we don't care what happens inside. Then if you go through this lemma, you will see that in a Knaser graph, the lemma rephrased is the bipartite induced matching number of Knaser graph Kg and K is at most 2K choose K, which is independent of N. Okay. In other words, you cannot find too large of an independent induced matching. A Knaser graph is small. this is all I want to talk about. About Erdős-Corrado, the intersecting family. Now we're going to move on to the next topic, the next, which is still a cornerstone theorem in extremal set theory, the Kruskal-Katona theorem. So, let's consider a motivating problem. Consider the following problem. The problem is we're given the number of vertices and edges of a graph, and we ask how many triangles we must guarantee to have. So, given an m vertex, m edge graph, how many triangles it must contain? This is the question. In other words, we're given number of vertices and number of edges. And what we want to do is to minimize the number of triangles. Okay. When the number of edges is at most n squared over 4, this is easy. The minimum triangle is just 0 by Mantel's theorem. We can use complete bipartite graph or subgraph of it. But when you go beyond that, things becomes difficult. And it is indeed a difficult problem. It took a long time to resolve. This is the famous Erdős-Rademacher Rademacher-Clique minimization problem. Yeah, we're given vertice, given the order and edge density, we minimize clique, number of clique, from 1940s, from a while ago. Long story short, this is difficult, only recently resolved. The asymptotic version solution is only recently resolved by Rasparov for triangle case, Nikiforov for triangle and K4, and about 10 years ago by Christian Raya for all cliques. And the exact solution only in the triangle case is known. This is by myself, Oleg Piherko, and Catherine Staden. This is the triangle case. So this is a difficult problem, but one can ask another natural question. What if we given the number of vertices and edges, we want to maximize the number of triangles? And turns out this variation is simpler. Well, I wouldn't say simpler, but we do have a complete answer of it. So So another natural question is, given number of vertices and number of edges, and our goal is to maximize the number of triangles. Okay. We will see that this is, we should see that this is the answer is provided by Kruskal-Katona that we will see. So what is Kruskal-Katona? This is to give you some motivation. Kruskal-Katona involves a new family So J1 in the chat says, for the maximization problem for triangles, perhaps a complete subgraph. And yes, the short answer is yes. That's correct. The intuition is that we want a very packed substructure to increase the number of triangles. We want to put the edges. We have a given amount of edges. We want to pack them as tightly as possible to increase number of triangles. And the tightest we can pack it into is a complete subgraph. And now the question is, what if the number of edges is not of the form some natural number choose 2? Then you cannot pack it to a complete graph. What are you going to do? Kruskal-Katona is going to give you a complete answer. So we have to first introduce a notion called shadow. Here's the definition. The shadow of a K family actually, let me switch to hypergraph language. So let's call it K graph. That means K uniform hypergraph. So a shadow of a K graph F on ground set N, you choose size K hyper edges, which we denoted by partial F. It's a K-1 graph, one uniformity lower is the K-1 graph consisting of all K-1 sets that lie in an edge of F. So in other words, partial F, let's write down it mathematically, equals to all those K-1 sets such that F it's a subset of some sets G where G is a hyperedge in our family F. Okay. Here's an example. Let's see an example. Let's take K equal to 2. Let's take C5. So a 2 graph is just normal graph. If this is G, if this is F, then what is the shadow? The shadow, if F is a graph, let me just use G then. It's a graph. Then the shadow of it, anyone? The original one is a graph k equal to 2. So the shadow would be one uniform hypergraph, which are just set of singletons that lies on the edge of F. So it's exactly the vertex set of G. Okay? It's vertex set of G, assuming G has no isolated vertex. No isolated vertex, so every vertex degree at least one is adjacent to some edge, so it lies in some edge, it lies in the shadow. Very good. This is not so hard for you, one uniform, isn't it? So let's look at 3 uniform. For 3 uniform, let's just draw, okay. I draw something random. So this is a hyperedge. This is a hyperedge. Yeah, let's draw a pretty one. Like a triangle, right? The hypergraph version of triangle like this. So this is my F, which is a 3 graph. So the partial F, it's a normal graph. Okay. How does it look like? Let's draw it. So here, well, we look at all the pairs that lie in the 3 edge. So this pair lies in 3 edge, this pair lies in 3 edge, this pair lies in 3 edge. Okay. For example, these 2 pair does not lie in any edge. So you don't, that's not a shadow. All right. You should ask question if you there. Yeah, good observation. So tier 1 recall that in one of the previous homework, we compare the shadow with the family itself. I don't remember if in the homework I defined the shadow to be the, let me check. Yeah, that's the shadow. Good. And you can now use, it probably follows from Kruska-Katona. I will leave it for you to check. So, good. Now the question that Kruska-Katona theorem is concerning about is, given the hypergraph, and we know how many edges in this hypergraph, then we want to minimize its shadow size. How small can it be? So the problem that Kruska-Katona want to study is let we have k uniform hypergraph on m vertices, and you have m edges, and at most between 0 and n choose k. What is the minimum shadow size of an m vertex k graph with m edges? Okay, this is the problem. In other words, we want to minimize shadow. That's the key word, right? So when you encounter a new type of theorem problem, a good way to digest it is to go through examples. Sometimes it might look stupid to try some small examples, but this process actually deepens your understanding because you have some concrete picture in your mind. So let's actually take the time to try some small examples to appreciate and understand Kruskal-Katona better. So let's do the same thing as above. We're going to look at the two simplest cases where we have two uniform normal graph and look at its shadow. And then we look at three uniform and we look at its shadow. All right. So let's look at two uniform, k equal to 2. This problem is relatively easy. So now if we have a graph G, that's just a graph, and let M to be the number of edges in the graph, and let's say there's no isolated vertex, in G, then we know, as we observe above, that the shadow of this graph G is nothing but it's the number of vertices in this graph G. Okay, all the vertices. So that means what we need to do now is to minimize the number of vertices n, given that we have m edges. Then exactly as Jie mentioned earlier, what we need to do now is to use as few vertices as possible to accommodate m edges. And the best we can do is pack them like a clique. And the best we can do is m must lies in some let me not write this n, right? We want to minimize the number of vertices given number of edges. M must lie in some two numbers. Let's say R choose 2 and R minus 1 choose 2. There must exist an R. And notice that if R is chosen in this way, M edges cannot be packed into a complete graph on R minus 1 edges, vertices, because of this strict inequality. So we have to use at least R vertices. That's the minimum. Best we can do is R vertices where R satisfy this thing. All right. So for k equal to 2, it's easy. We solved it already. Any question? Now let's look at k equal to 3. It already becomes non-trivial. All right. Let's say our number of edges is 4. A simple case. Another example. M equal to 4. A 3 uniform hypergraph on 4 edges. We want to continue our intuition above. We want to pack edges as tightly as possible, right? So we would like to pack hyper edges as compact as possible. This is the intuition. So for 4 hyperedges, well, 3 uniform hypergraph, if you have a single edge, you must use 3 vertices. Okay. The moment you have 2 hyperedges, you need a new vertex. You need to introduce a new vertex. Then you put these 2 edges, right? One is this hyperedge, one is this hyperedge. And now, it's better to introduce a new vertex and make use of the previous vertices. Because if the 2 edges you have are disjoint, then the shadow size immediately becomes 1, 2, 3, 4, 5, 6. You have 6 pairs lying in the shadow, so that's bad. But if you make use of the previous 3 vertices and you introduce a new edge like this, then what's the shadow size now? 1, 2, 3, 4, 5, right? It's smaller than 6. And it's not hard to check that this is best possible. Now we're going to continue as before. You want to pack the 3rd edge also on this quadruple. Because if the 3rd edge has new vertices outside, you're going to definitely introduce some new pair in the shadow. Here, I introduce 3 new pairs. If I introduce a new one outside, a new vertex outside, you're going to introduce at least 2 new pairs into the shadow. So we must choose a triple that's already on the existing ground sets. And by doing so, we only introduce this new pair into the shadow. Okay? So a moment of thought, which is what we just did. Tetrahedron, exactly. Tetrahedron is the best we can do. All right. Good. But now, what if we go higher? Again, 3 uniform. Well, now we have 7 edges, let's say. We already know for 4 edges, the best we can do to minimize the shadow is to take the tetrahedron. So let's write it like this, draw it like this. We have all triples on these sets, okay? All the triples on these sets. And this one, all right? So the tetrahedron here, we have 4 edges. We need 3 more edges. So here, it's not the precise proof that why we should build upon this, but let's use our intuition. Let's say we pack 4 as compactly as possible into tetrahedron. We need to put 3 more edges. So what's the best way? Well, and here the shadow for these 4 edges is 6, right? I forgot to write shadow size equal to 6. Now, if the 5th edge is completely disjoint from the previous 4 vertices, again, it's bad. Right? We introduce 3 new pairs into the shadow. But we have to introduce a new vertex, haven't we? Don't we? Because all the triples on these 4 vertices are taken. So to introduce a new triple as a hyperedge, beyond 4 edges, we need a new vertex. But we don't want to use 2 new vertices or more. If you use 3, you introduce new 3 pair. If you use 2, you use 1 there, right? Then you introduce, again, 3 new pair. If you just use 1 and use some existing pair inside the 4, then you only introduce these 2. Okay? So we have to introduce a new vertex. And we want to make use of this is hyperedge. The edge, the shadow that we introduce is this one and this one. Now, if you want to go another hyperedge, what do we do? Again, you don't want to choose, we don't want to introduce a new one because the new one will introduce again the 2, right? We don't want to use this new vertex with 2 new vertices in that are previously not used, because again, introduce 2. But look, if we take this hyperedge, we only introduce this pair as the new pair into the shadow. That's more economic, all right? So let's try. The next one is you take this one. Then you introduce this pair. So now we have 6 edges. The 7th edge, what do we do? Well, we get one for free because what you can do is you can take this hyperedge. What happened is this is, for this hyperedge, this is already in the shadow, This is also already in the shadow. You get it for free. The 7th edge, we get it for free. Okay. Cruz-Catona is saying that this way of packing things is the best we can do when minimizing the shadow. So this is called, there's a name for this ordering. This name is called colexicographic order. So let's define this thing, definition. This is the colex order definition. If you have 2 distinct sets, K sets, A1 to AK, and B is B1 to BK, of natural numbers with increasing order. Okay, then we say A is less than colex less than B if so how do we compare them? The larger one, we compare them, we go from right to left. You compare the first digits from right to left, which one is larger? The larger one is larger. If they are the same, move on to the next one. If this one is larger than the next one, then B is larger. In other words, if AJ, if AI is less than BI, where I is the max. Let me maybe use a different symbol. AS is the where J is the max index where they differ. Okay, in other words, informally comparing them from right to left. Okay, comparing them from right to left. Look at the first position, the largest position where they differ. Look at the largest position where they differ. And the larger one on that position is larger. In collex. So if you're familiar with lexicographic order, collex is comparing from right to left, whereas lex is comparing from left to right. That's the dictionary order. But we're now working with lex for now, so let me not confuse you with a different one. So let's just remember informally, this is comparing from right to left. Let's do an example of these initial segments. Initial segments of collex for k equal to 2, shall we? So for k equal to 2, let's write it in binary string. Two sets of natural number is basically a binary string where we put 2 ones. If I take 1, 2 is a set in our family, we're going to write it as 1, 1, 0, 0, 0, 0. This is coordinate 1, coordinate 2, 3, and so on and so forth, right? You can match it like this. So the initial segment will be, well, we want to compare from right to left. So let's just write out 5 digits. If you just write out 5 digits, you want right to left, the smaller one, that means you want to use 0 as many as possible from right to left. So the first element is 1, 2, which is 1, 1, 0, 0, 0. This is 1, 2. Then we have to introduce a 1 here. And we want to postpone using 1. We want 0. Postpone using 1. So we can put 1 here. This is correspond to set 1, 3. 0, 0. We have to use 1 here. Then now we cannot postpone 1 anymore. We have to put 1, 0. This is 2, 3 sets. Now the first 3 position we exhaust all two sets. We have to now introduce a 1 here. We can postpone 1 to the first position. So this is 1, 4, and so on and so forth. Okay? The rest is easy. I will just write down all of them. Now 1, 0, 0, 0, 1. 1, 0, 0, 1, 0. 2, 5, right? 3, 5. And the last one is like this. Okay? This is 4, 5. So on and so forth. And Cruz-Catona theorem, now I can state it. Let F be a K-graph with n choose K, n sub K choose K plus n sub K minus 1 choose K minus 1, n sub S choose S, where n sub K bigger than n sub K minus 1 bigger than n sub n sub S. Okay, then the shadow of F. So this size, we write in this size to match to our intuition. What's the intuition? First, we pack as many as we can. In the first nk, use the first nk elements. Once we exhaust them, because the m size must be between some nk choose k and nk plus 1 choose k, right? Between these two. So we exhaust all the k elements in the first nk ground set elements. Then the remaining, what do we do? Well, we first exhaust again the colex initial segments in the link of a vertex, which is what we did here. If you look at, we introduce this new vertex. You look at all the next edges we introduce, they form a colex initial order, initial segments in the link of this vertex. You want to introduce a new element once again and pack, and the new edges we introduce. If you delete these new elements, we'll pack as tightly as possible, but one uniformity lower in here, right? So let's look at example 1. Let me write. Note that in example 1, this is, we have colex order. And the link of one feature is that the link of a new vertex introduced is also ordered in colex, but it's in terms of k minus 1 sets in the link, right? What's the shadow then? In this example, N3, 3 uniform, right? Equals to 4. You have these 4 vertices. You choose all 3 in there. M equal to 7. K equal to 3. N3 equal to 4. N2 equals to what? 3, right? So 7 can be written as 4 choose 3 plus 3 choose 2. Okay. What's the size of this shadow? The shadow size is on this 4, we have all the pairs. So it's 4 choose 2 plus on this 3. These are already counted. So we just need to count these 3, which correspond to singletons on these 3 sets. So it's N2 choose 3 minus 1. Sorry, 2 minus 1 plus 3 choose 1. The singletons on these 3 sets. Okay? So in general, for colex, we can write its shadow size to be nk choose k minus 1 plus nk minus 1 choose k minus 2 dot plus ns choose s minus 1. Here, I'm assuming something. I assume that every m can be written in this way. In what way? For every m, we can choose nk minus 1 to ns, satisfying these such that we'll leave it as exercise to show that for every m, k, natural number, there exists a unique way to write this. Okay, there's a unique way to write it like this. This is not hard. And if you write it like this, this right-hand side, the shadow size, equality holds for initial segment of colex order. Remark. This bound is best possible. Equality holds for initial segment in colex order. Any question about the statement? Okay, let's look at the proof if there's no question. So here we going to introduce a very useful combinatorial technique called shifting. Sometimes people call compression. It's called shifting or compression in the literature. What's the philosophy of this shifting compression? Every time shifting compression might look slightly different, but the philosophy is that the idea is that we have some extremal problem for sets, extremal set theory problem. And this problem is for generic families. We're gonna do some operation so that we can reduce this extremal problem from, so that it was originally for all families, with all general families. We can reduce this problem to some special families. And I want to reduce it to special families that are highly structured, so we can make use of the structure. That's the idea. The idea of the shifting method is to reduce an extremal problem, which initially is for general families, to some special family that are highly structured. That oftentimes makes the problem easier because initially you want to maximize some invariance over all families. Now you just need to maximize this invariance, this parameter, over a subfamily where we know how this subfamily look like. And what we're going to do here already, this statement suggests how the shifting should go. We know that given a K-uniform family, a K-graph, given its size, the shadow is minimized. The minimum is this quantity, which is realized by Collatz order, the initial segment. So the proof idea is that we start with the K-graph F. We're going to massage, we're going to use shifting to change this family into the initial segment of the Collatz order. And when we do this massaging, shifting, we want to keep the size of this family unchanged because this is the hypothesis. We're given the size of this family, the size of the hypergraph. Furthermore, we do not want to decrease its shadow size while shifting, while shape-shifting this family, right? So for Kruskal-Katona, what I just said is, for Kruskal-Katona, it suffices can someone tell me how to disable this thing on the pen? It keep popping up. So for Kruskal-Katona, it suffices to have a shifting operation that change F to initial segments of Collatz such that we need to keep two things. Size of family unchanged. Let's say initial segment, which is I, right? So F equal to I. No, I shouldn't say F equal to I. During this process, the size of the family is not changed, and the size of the shadow not decreasing, not decreased. Okay, once again, if you have F, I change it to some G such that they have the same size, and the shadow of G, should I say not increased? I'm getting confused. One second. Not increasing the shadow, okay? Because we want the lower bound, yeah, right? Okay, let me write more precisely. So you're going to change, let's say, to F1, F2, dot, dot, dot. At the end, you change to this. Let's write more careful. At the end, you reach this initial segment I, right? So size unchanged, so F equal to F1 equal to F2, dot, dot, dot. Right? The size of shadow not increased. That means what? The shadow of this is at least the shadow of F1, which is at least the shadow of F2, dot, 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 dot. At the end, shadow of I, which is the Kruskal-Katona bound. That's what we want to do. Then we have what we want, right? So here's the shifting operation. In this case, given F a uniform hypergraph and some index I between 2 and n. For any sets or hyperedge in our family, we define the shift which is as shift the i's index of this set F to be what? What we're going to do is we prefer smaller elements than large elements. So shifting on I, that means we're going to delete I from F, and we're going to add 1 to F. Okay? Add 1 to F. If I is in F and 1 is not in F, and also this new sets is not already in the family. If this new set is already in the family, we don't do anything. You just keep it the same. Let's draw it in binary strings to see how this operation works. So we can think of F as a binary string of think of it as a binary string with k1s. The k1s stands for the elements inside this k set F. So F looks like this. These are the coordinates. F does not contain 1. F contains I. The others, I don't care. We want to change it to this guy, which is minus I union 1. That means maybe I should use a different color. That means when you see a set F, doing the I shift is to switch 0 and 1 on the 1 and I's position, provided that this new string is not already in your family. Then you do the shift. Otherwise, you remain the same. I'm running out of time. I think I will continue next time. So today, what we did, let's summarize. Number of maximal intersecting K family, while Bolobash set pair and Kruskal-Katona. Okay. Any question? So I would suggest, if this exercise is not clear to you, I would suggest you to work out the details to show that every number can be write uniquely as this combination of binomial coefficients in Kruskal-Katona. And then if this is not clear, that it's the shadow size over initial segment of this size, I also encourage you to work out other examples than this one to convince yourself that this is the shadow size of the initial segment. All right. Today is Tuesday. So if there's no question, I will see you guys on Thursday. On Thursday, I would make some announcements on the logistics for final exam.